Hello friends, I welcome you in lecture number 16 on vector calculus. In lecture number 15, we have talked about path independence of line integrals, and we have seen that if our vector field f bar is conservative, then its line integral is independent of path. If f bar is a conservative vector field, then the line integral of f bar along any curve C joining given two points, say A and B, has same value. If we take any curve, say C1, C2, C3, if we take any curve joining two points A and B, then this line integral is independent of path between these 2 points if our vector field f bar is conservative. And if we have conservative vector field, then f bar can be written as gradient of some scalar function, say f of xyz. And if our vector field is conservative vector field, this line integral is independent of path joining 2 points A and B, and the value of this line integral along any path C joining 2 points A and B is given by value of this potential function at terminal point minus value of this potential function at initial point, and this result is known as fundamental theorem for line integrals. We have discussed about all these things in lecture number 15. So if you have not seen lecture number 15, I suggest you to go for lecture number 15 first before going for this lecture. And in this lecture we are going to discuss one example related to this fundamental theorem for line integral. Another thing we will understand is, suppose I have a vector field f bar with three components, say f1, f2, f3, and if we are working in R3, that is in space, we will consider dr bar equal to dx, dy, dz, and dot product of f bar and dr bar will be equal to f1 dx plus f2 dy plus f3 dz. And we know that we can write line integral in different ways. We have different notations for the line integrals. Instead of this notation, we can use this notation also, f1 dx plus f2 dy plus f3 dz. Now this f1 dx plus f2 dy plus f3 dz is differential form because it involves differentials of x, y and z. So we will call this form as differential form. Now this differential form is called exact differential form if our vector field f bar is conservative. And if vector field f bar is conservative, line integral is path independent, or line integral has the same value along any path joining 2 points. So remember this another word also, exact differential form. Sometimes they can ask you to prove that this differential form is exact and then evaluate the line integral. So to prove that differential form is exact, it is enough to prove that vector field is conservative, that is its curl has zero vector. So we remember this as a remark. Let f bar equal to f1i plus f2j plus f3k be a vector field. The differential form f1 dx plus f2 dy plus f3 dz is exact if f bar is conservative on a given domain D. And if the differential form is exact, then line integral is independent of path in a given domain D. This line integral we can write in this way also. F bar dot dr bar is f1 dx plus f2 dy plus f3 dz. To prove that this differential form is exact, we will prove that this f bar is conservative vector field, and we know that if f bar is conservative vector field, line integral is path independent. So we discuss one question related to this. This question show that 2xyz dx plus x square z dy plus x square y dz is exact, and evaluate the integral between 2 points 1 1 1 minus 1 2 2 over the line segment from this point to this point. Here we are asked to find out the value of this line integral, and along the line segment joining 2 points 1 1 1 and minus 1 2 2, and we can rewrite this differential form as dot product of these two vectors 2xyz x square z x square y. If we take dot product of these two vectors dx dy dz, then by the definition of dot product, this is 2xyz into dx plus x square z into dy plus x square y dz. So instead of writing this dot product, they have given this in the form of differential form, and they have asked to prove that this differential form is exact. So we will consider this vector as vector f bar, and this is dr bar, and to prove that this differential form is exact, we will prove that vector field f bar is conservative, and we know how to prove that vector field f bar is conservative. We know that vector field f bar is conservative if it is defined at every point in R3 and its components have continuous first partial derivatives, and curl of f bar is a zero vector. So first we mention all these things. Vector field f bar is given by this, and all these components are polynomial functions. Therefore f bar is defined on all of R3, that is f bar is defined at every point in R3, and polynomial components are always continuous, their partial derivatives are also continuous, so that we have written here, and its components have continuous first order partial derivatives. We require first order partial derivatives to be continuous, and they are continuous obviously because derivatives of polynomials are also polynomials. And then we find out curl of given vector field f bar. By the definition, curl is given by this determinant. First row is vectors I, j, k. Second row is components of del operator. We know that this is nothing but dot product of del operator and vector field f bar. So this second row is components of del operator, partial derivatives with respect to x, y, z, and then components of vector field f bar. So we have written these three components 2xyz x square z x square y, and we evaluate this determinant. First we consider determinant of this 2 by 2 matrix multiplied with vector I. So I have to differentiate x square y with respect to y. X square is constant, derivative of y is 1, so we have x square minus derivative of this x square z with respect to z, which is x square. So here we have x square minus x square times I, then minus j into we have to consider this now, minus j into partial derivative of x square y with respect to x, which is 2xy, minus partial derivative of 2xyz with respect to z, which is also 2xy, and then k times or determinant of this matrix, that is partial derivative of x square z with respect to x, which is 2xz, minus partial derivative of 2xyz with respect to y, which is 2xz, and finally we have a zero vector. Therefore curl of f bar is a zero vector, and therefore f bar is conservative, and therefore this differential form is exact. And we know that if we have conservative vector field, line integral is independent of path joining 2 points. Here we are asked to evaluate the line integral along the line segment between these 2 points, and we have shown that this differential form is exact, or we have shown that this vector field is conservative. Therefore this line integral is same along any path joining 2 points. And if our vector field is conservative, we can write our vector field as gradient of some scalar function f, and the value of this line integral will be equal to value of this potential function at upper point or terminal point minus value of this potential function at starting point. So we have to decide this potential function for the conservative vector field. So now we try to find out potential function. Since f bar is conservative, f bar can be written as gradient of f for some scalar function f of x, y, z. Then we write down two vectors. F bar is, we have written given vector field, and gradient of f is del f by del xi plus del f by del yj plus del f by del z k. And we know that two vectors are equal if their components are equal. Therefore del f by del x will be equal to 2xyz, del f by del y will be equal to x square z, and del f by del z will be equal to x square y. And we obtain first order partial derivatives of function f of xyz, which is potential function for conservative field. Now to obtain this function, we can start with any of these three equations, and suppose we start with equation number 1. Then to obtain function f, I have to integrate this equation with respect to x on both sides, and I will consider y and z as constants. Therefore constant of integration will be a function of y and z. Instead of writing constant c, we are writing some function of y and z, say g of yz, because while integrating with respect to x, we treat y and z as constants. So the terms which will contain y or z or both will be considered as constants. Therefore constant of integration will be written as some function of y and z. Now this integral will be our function f of x, y, z. Here integral is with respect to x. We will consider 2yz as constant, and integral of x is x square by 2. So that I have written here 2yz x square by 2 plus g of yz. These two will cancel out, and we will obtain f of xyz equal to x square yz plus arbitrary function of y and z. Now this is not complete information about potential function. We don't know what is this function. To obtain this function, now we can use either equation number 2 or equation number 3. If you want to use equation number 2, we have to differentiate this function with respect to y, so that we can put value of del f by del y. So in the next step, we differentiate this equation number 4 with respect to y. Left hand side is del f by del y. Here x square and z are constant because we are differentiating with respect to y partially. So x square z is constant, derivative of y is 1. G is function of two variables y and z, and we are differentiating partially with respect to y. So here we will write del g by del y, and in the next step we substitute value of del f by del y, which is x square z. So we put value of del f by del I, which is x square z, that we write from equation number 2. So in the bracket we mention that using equation number 2, and this is also x square z. So therefore partial derivative of g with respect to y will be 0, and g is a function of y and z. So to obtain value of g, again we integrate both sides with respect to y. If we integrate both sides with respect to y, left hand side will be g of yz. Integral of 0 will be 0 plus constant of integration. Now g is function of y and z, and we are integrating with respect to y partially. So terms containing z will be considered as constants. So instead of writing plus c, we have to write some function of z. So therefore g of yz equal to h of z, and this we substitute in equation number 4. So our scalar function will be now f of xyz equal to x square yz plus h of z. So that we have written here. So this is our potential function now. But still this is not complete information about potential function, because we don't know what is this function of z only, that is h of z. So to obtain h of z, now we will use equation number 3, which we have not used so far. So for that we have to differentiate that equation with respect to z. So in the next step we differentiate both sides partially with respect to z. Left hand side is del f by del z, derivative is with respect to z, so x square y is constant, derivative of z is 1 plus dh by dz, and now we are having this value del f by del z, that is x square into y. So that we substitute here. Del f by del z is written as x square y, and that we write using equation number 3. And now we can see x square y equal to x square y plus dh by dz. Therefore dh by dz will be equal to x square y minus x square y, that is 0, and this h is function of z only, whose derivative with respect to z is 0. Therefore h must be a constant function. Therefore h of z equal to c, where c is a constant. So finally we have obtained value of h also. So our potential function will be f of xyz equal to x square yz plus c, and c is constant of integration. So this is the complete information about potential function for conservative vector field f bar. Now once we obtain this potential function, we will apply fundamental theorem for line integrals to obtain the line integral of given vector field. Our line integral is given in this form, differential form, and we have these 2 points 1 1 1 and minus 1 2 2. We are asked to find out line integral along the line segment joining these 2 points, but we know that this line integral is independent of path because vector field f bar is conservative. Therefore value of line integral along any path, not only straight line, along any path joining these 2 points will be equal to value of potential function at terminal point minus value of potential function at initial point, and we have obtained the potential function, and we have to decide value of function f at point minus 1 2 2 and at point 1 1 1. So in this from this equation we can decide what is f of minus 1 2 2. So I have to put x equal to minus 1, y equal to 2, z equal to 2 and plus c. So that I have written here. Our function f is x square times yz plus c. So first we put x equal to minus 1, y equal to 2, z equal to 2 plus c, and minus value of function at 1 1 1. So 1 square 1 1 plus c, and this is 4 plus c, this is 1 plus c, and we have to take subtraction, so c will cancel out, and we obtain that line integral has value 3. So this is very important step. Here we are asked to obtain the line integral along line segment joining 2 points, and we are not using the equation of line between 2 points. Instead of that we are using the fact that our f bar is conservative, therefore this line integral is independent of path. So we are not doing any parametric representation, or we are not writing even the representation of line segment, or we are not writing the equation of line joining 2 points. we are not uh, writing any information between the curve joining these 2 points, which is line segment, because we know that line integral is independent of path. Therefore value of line integral along any curve joining these 2 points will be same, and that same value will be equal to value of potential function at terminal point minus value of potential function at starting point by fundamental theorem of line integrals. So if you are not given that along which curve you have to integrate, sometimes they will ask you to find out the value of this line integral along any path joining these 2 points. If your integral is independent of path, then you have to go in this way. So here first we prove that differential form is exact. For that we prove that f bar is conservative, and once we know that f bar is conservative, we can find out its potential function, and once we obtain potential function, the value of line integral between 2 points along any curve between 2 points is obtained by value of potential function at upper point minus value of potential function at lower point. And in our case, our line integral has the value 3 along any path joining 2 points, not only this path which is a line segment. Along any path joining these 2 points, the value of line integral will be 3 by fundamental theorem of line integrals. So this is very important problem. They can ask you to find out this type of they can ask you to solve this type of problems. So you can check whether your differential form is exact, or you can check whether your vector field is conservative, and if it is conservative, your line integral will be path independent. So in that case, you decide the potential function for your vector field, and you can easily obtain the value of line integral simply by finding the value of potential function at upper point and at lower point, and then taking their difference. So this is all about this session. We will discuss one more problem of this type in upcoming lecture. Thanks for watching.